So let me first say good morning to all of you. And it's pretty early morning, so I hope that I wouldn't take your uh, things so much off, and I should be taking time 75 minutes. And of course, I'd like to thank Pradeep and other people in this organizer to make this thing to happen and invite me to give this lecture here. And I make this lecture somewhat pedagogical, not too much getting into details of research that we are doing based on those things. I shall of course touch upon them. So because my primary audience are students, I divide my talk into few modules. The first module I shall talk about what is a simulation, why the simulation is being done, and what are the algorithms to do simulation. Next, I shall go how the algorithm is developed for protein simulation, for example. But protein simulation, I'm sure all you guys will agree nowadays that is a tough job. And to understand protein in a deeper way, as a physicist, okay, I'm a physicist, of course. As a physicist, will like to see you cannot really do normal protein simulation that people do. You have to develop some smarter scheme to understand for example, the phase behavior of a protein, okay, a protein solution for that matter. Okay, so this work has been done entirely in the Essenbo Center, National Center of Basic Sciences. Over the years, actually, we have started doing this calculation at least now 7-8 years back or even more. So much before the corona came in. So something about, I will say 10 years already. Okay. So let me just first focus on what is simulation. If I describe simulation in a nutshell, I will say this is just numerical experiment. Now you might ask, why numerical experiments? You do experiment, you do theory, then why numerical experiment all of a sudden comes in? It's something a bridge between the two. See, in experiment, what happens that you do experiment, but controlling the environment to perform some experiment and get some result which is interpretable becomes difficult. On the other hand, when we are doing theory, you can have an idealized condition. Like simple example that when we talk about some property of material, we assume that the material is infinitely long so that you can apply all the thermodynamic rules and calculate its properties. But this is seldom correct. And so both ends have got their own caveats. Now, numerical experiment bridges the gap between the two in the following way. First of all, it is on computer, hence controlling the environment becomes pretty easy, that's in your hand. And once you do the control experiment numerically and try to see if it matches with the experiment, then you're pretty happy. You say, well, the experimental system, despite limitations of experiment, mimicking this kind of behavior, which follows from this kind of model. That's one side. Second side is that if you know the model better, then you can compare the theory and see under what condition theory should be improved so that your prediction becomes better and it agrees with experiment in a better way. So it's a kind of a thing which has got limbed into both sides. And no wonder that there's a development of current matter physics depends a lot on numerical simulations like this. And now with this preamble, there are caveats, I'll come back to that. It's not that simulations does every magic for you. There are problems, there are subtle things which one need to consider. So, but before I go to that, let me tell you, there are two different types of simulation that we normally perform. Now, numerical simulation is something we require. You can understand, pretty from your, bachelor's program. See, when you calculate the classical mechanics trajectory of some particle, you can calculate the trajectory for one single particle. You cannot go beyond that. So you might ask, oh, we solved the central force potential, right? Those who are from physics will appreciate that we solve harmonic oscillator problem and we take infinite long harmonic oscillator chain. then all the infinite number of particles. But you have to understand that for such problems, the Hamiltonian is such that, I guess Hamiltonian is fine with all of you, right? Is such that you can divide the Hamiltonian into single particle level. And you solve each of them and get final solution for the entire system. In the end, you're not solving the infinitely many harmonic oscillators. You're just solving one particular problem, and that's the normal modes actually. All right. Now, in practice, what happens, however, the system that we look into, we know they have Avogadro number of particles, right? So we normally say, 1 is fine, 2 is the company, 3 is the crowd. In fact, that is so true about physics. If you have a third particle, you are just doomed. There is no solution that one can write in a closed form that will solve for 3 particles. And forget about Avogadro number of particles, which can be about 24 number of particles. So obviously, in order to understand how a particle at the molar level, a system at the molar level is going to behave, you have to know the trajectory. There's no other go. But looking at the trajectory is a big challenge because we cannot calculate the trajectory in closed form. And hence the numerical things goes in. That we use computers to calculate trajectory for many particles. But there's a limitation in the following sense. We are far behind the Avogadro number. The maximum number you can try to simulate that way, even with GPU, is not really more than a few millions. A million is 10 to the power 6, Avogadro 10 to the power 24. You see the gap. Okay, therein lies a lot of problem actually. But anyway, so basically, you have to compute the calculation, the trajectory in a numerical way. But then you have to be extremely careful. This is something I'm trying to explain here. So, we know of this equation of motion for ages, already for more than 400 years. But the computer simulation, first successful computer simulation came up in a year even after my birth, and that is 1969. So then what is the reason for doing so? People have known, thanks to Newton, a lot of numerical techniques was developed by Newton to calculate the orbits of different planets. But even then, there was difficulty. If you take, I'm sure that you guys know how to solve the differential equation. In the end, okay, Newton's law gives a differential equation, right, for the trajectory, which is second order differential equation that will solve. Now, there are ample number of methods nowadays that you can solve the second order differential equation. Runge-Kutta is something all you guys know, right? The problem is, in Runge-Kutta, you can solve the differential equation. But when you're trying to look at the dynamics of a system, then something more you have to look into. So the way that you have to think in the following things. First, for a dynamical system, we know that there are some conserved quantities, right? Energy must be conserved, momentum must be conserved, and the dynamics can be reliable only when your trajectory satisfies the conservation laws. Otherwise, you can calculate any damn thing on the earth. That's all nonsense. So you have to devise your numerical algorithm in such a way that the conservation laws are being followed. So first successful such thing came by Varley, and if a Varley algorithm is still used, so no matter fancy things that you do on computer using GROMACS, using LAMS, using all these things, they're all based on Varley algorithm. Now, what is the idea of Varley algorithm? First of all, if you look at a trajectory, you assume that the trajectory is a continuous function of time. Everything classical, no quantum mechanics in it. So you can write a Taylor expansion for the trajectory. Let's say the Taylor expansion, something right? You can write the some functions as a power series of deviation from certain origin. So here delta t is the deviation in time from t equal to 0, which is the initial time. And you can again write down something like this. Now you see that if you truncate right here, so you can say, well, I have an equation here. I know what is the velocity. This vt is velocity, and 8 is acceleration. If you know the force law, like you know that m times acceleration is equal to force. So if you know mass, if you know the force, then you know the acceleration. So everything is fine. So you can write this, and now you see that this is essentially propagation in time in a forward direction, and this is propagation in time in the backward direction. So things should be fine. So if I just use this equation, I should be able to solve the trajectory. And that's people thought for a long, long time. And it doesn't work. You know why? Simple reason is, since you truncate, there's no guarantee that energy will be conserved. So, and as an illustration, you see that when we were at the +2 level, we used to show that the energy of a harmonic oscillator is conserved, right? So if you take the simple pendulum, at any point the energy is the same. But don't forget, while showing this, we required the trajectory of the harmonic oscillator. So we took x equal to a sine omega t. We put the solution into the energy expression, which is kinetic energy plus potential energy, and then we could show that this is conserved. So in order to show there's a conservation, energy is conserved, for example, you need to know the trajectory exactly. There's no other go. This is all mathematics. There's no physics, no hand waving in this. Now, since it is approximate, after all, Taylor series is an infinite series. And we're just truncating at some point, let's say. Why truncating here? Because we do not know what will happen to the third derivative and so forth. So we just say, okay, you don't care about it. So if I take till this, energy conservation is not guaranteed, okay, because your trajectory is approximate. So the question is, and not only that, if you reverse the sign, that's what I wrote here, you know, the trajectory is not the same as this one. But we know in Newtonian mechanics, for example, is time invariant. No matter what time direction that you take, the same equation of motion will follow. So if you go in forward, then you can also come back backward in the same trajectory. It is not followed here. So we call technically the time reversal symmetry is broken. Okay. Now the question how to revive. So that's Varley did. If you add these two terms, you get something like this, right? Now, if you truncate a second order, then you see that you're doing error, no doubt about it. Any numerical calculation you do based on some approximation to the trajectory is an error. There's no doubt about it. But is the error allowable? Shall we be happy with that error? And the point is that for this, let's say, updating rule, you are truncating second order, but the error is happening at the fourth order. Can you see why? Because you see that you have all the terms here, and then if you add them, all the order terms vanish. So the term, so even though you're writing like square here, the error that you're committing at the fourth order, because that is the term that you're ignoring. So am I clear to all of you? Yes?
You may have to run through once again, I think, because several people came fresh.
Oh, okay. All right. So to be to make the things slightly more precise and abridged, we are writing down the trajectory as some expansion in time difference. And if you take a simple time difference like this and truncate at the second order, because we know the velocity, we know the acceleration from the force law, the problem that arises that the trajectory becomes so inaccurate that energy conservation becomes a problem. It may not satisfy energy conservation, and typically it doesn't. And not only that, if you reverse the sign of delta t, then the trajectory is not traced back. So these two, fundamental, let's say, aspect of dynamics is being violated. Now, if you take what Varley actually proposed, he had taken these two form and then added them. If you add them, you get again time translation, but since you are adding them, all the odd order terms having negative sign, they will cancel. So if you truncate at the second order in time difference, then actual error that you're committing is at the fourth order, as a result of which your trajectory becomes accurate till 4th order, not at the 3rd order. Okay, so here, if you truncate here, then this is accurate to 3rd order because you are ignoring terms with delta t cube. Here, you don't have cube term at all, so you are actually truncated the order of delta t to the power 4. Now, it turns out that this is good enough to ensure energy is conserved. And that's the first breakthrough that Varley did in 1965. And then you see that if you change the delta t, the time universal symmetry is maintained. There is no change in sign anywhere. So this was the algorithm that was used by Varley and later by other people, and there was successful simulation that was reported in 1969. Okay, and if you subtract them, then you get velocity, but velocity is less accurate. You can see because if you subtract, all the even order terms will vanish. So this is accurate to cubic power. But the most of the time we are sort of more bothered about the potential energy part, and that is sort of better is represented in this form, and as a result of which this appears to be a reasonable, let's say, algorithm to work with for doing computer molecular dynamics simulations. Okay, so now there's one more simulation scheme which I'm not going to elaborate here. I shall come back to this later. So this is something like, it is possible, look, when I'm doing molecular dynamics, we are calculating trajectory and we are computing the different properties of the system, let's say energy, pressure, etc., on different points of trajectory, and we are taking time average. So at different times we compute the quantity and take simple arithmetic average. And we just say that we assume that the system is ergodic. That means the time average and ensemble average are the same, provided your system is in a well-defined ensemble. Okay, so that's a basic thing that undergoes like any statistical mechanical theory that we do. Now, there's another method of doing this calculation is something on Monte Carlo. Now, Monte Carlo simulation is like the way is stochastic simulation. So, for example, that the system can have this much space and this much range of momentum, and then you assume that as the system evolves, that means at different time the system has got some position and momentum. Now, if you solve molecular dynamics, then this exploration into space, position and momentum is according to the dynamical rule given by the equation of motion as type of Varley algorithm. And here you have the Hamiltonian. So now you just say, if you go from one point to another point randomly, then I shall come back to this when I go for illustration, not in this slide itself. So as you go from one point to another point randomly, there's the energy cost because the value of the Hamiltonian need not be the same. So if the energy decreases by going from one point to another point, then it's favorable for the system, right? The energy decreases, right? And so you take that point as let's say the new position of the particles in the system. If the energy increases on the other hand, then you don't discard that move. You compute the Boltzmann probability of how much the probability that system can go from this point to that point as per the Boltzmann statistics. If the statistics allows that, then we take this point. If not, then we discard the move, we go for another move. Okay, so this is essentially what we perform in Monte Carlo. Now, Monte Carlo and molecular dynamics essentially gives same result because in molecular dynamics, you calculate the time average, and in Monte Carlo, you compute the ensemble average. Now, under certain, let's say, quote, these two results are comparable because of the underlying statistical mechanics of the system. We know that for ergodic system, if you choose, if you calculate the ensemble average and if you calculate the time average, they must be the same in thermodynamic limit. That's the main catch. Okay, but anyway, let's not bother about those technical things right now. So far what I said is the basic idea of computer simulation that is implemented to understand any condensed phase property. So for almost everything so far, you don't bother so much about the electron and how the electron transfer takes place, etc. This kind of scheme works for any system for that matter. What is the thing that you require to perform this calculation? You need to know force. So if you, or in other words, if you want to do Monte Carlo, then you need to know the Hamiltonian, which is the energy of the system. Okay, so either you should know the force or you should know the energy. This is where actually the main problem comes in. See, if you want to compute the energy or force, that's essentially coming because mutual interest between the particles. Now, if there are n number of particles in the system, then the number of mutual interactions will be how many? Can someone tell me? NC2. That means n into n minus 1 by 2. That's n square, right? The main computation cost goes in computing this particular part of the program. And the cost goes like n square. Now just imagine, suppose we have, let's say, 10 cube number of particles in the system. So then the cost will be like 10 to the 6, right? Now suppose you are, say, I'm not happy with this. I'd like to increase the number of particles to 10,000. Then you'd imagine, well, then 10 times, no, it was 10 square, right? I mean, so now the cost becomes 10 to the power 8. So even for 10 times increased number of particles, the computation cost goes the square of that. And there's nothing doing about it because you have to compute all the energies, all possible energies in the system. And there a lot of effort goes in to make this particular part of computation of energy or force, depending on which scheme that you're using, amenable by computers. So the parallel program that we nowadays we hear about is just to tackle this. Okay, how to tackle a situation where normal computation goes like n square should go like n log n. You see, log is a much less function, this thing, right? So this log n part actually, so now n square is n into n. Now you get n into log n. So one n is supplemented by log n. And entire industry, starting from let's say 1990s, has gone into how to improve this and make the computation log going like log n. We have been successful, not completely, but to some extent, by let's say CPU, GPU kind of stuff. So that's the basic reason why.
You should also know that Rahman is from Hyderabad.
Yeah, of course, yes. Yeah. Okay. Now, yeah.
Are you including skills as you have told earlier that you should follow distribution of Maxwell?
Well,
It's a classical approach. I think for me, Dirac and both Einstein.
no. This cannot be taken into here. Okay, it's just classical things. Okay. So even for classical things are difficult. Of course, nowadays people do quantum simulations, but that is much more difficult than this. I'm not going to do that at this moment. And I'm just restricting everything to the classical limit, okay? And even there you see that the world is really big, it's not that small, okay? And in fact, it's bigger, I'll tell you, because it's applicable to many systems actually. So the first simulation was reported by, was done by Anisul Rahman in 1964, okay? So this is the time where all these computers started coming in. Anisul Rahman first successfully did this calculation, and then of course he is regarded as the father of MD simulation, and there is a prize, is a prestigious prize named the Anisul Rahman Prize for computation. Now the first protein simulation came up 25 years later, and the simple reason is people had to work like hell to go from n squared to log n, okay? Now, let us now try to see why this business comes in. See, protein, for example, is not just protein, just an example, okay? There are many systems. The problem is there's an underlying structure. See, when we talk about, let's say, the Raman simulation that was performed, that was just taking argon. Argon has got no structure in it, it's an inert gas. and the interaction potential between argon is taken to Lennard-Jones type. It's very simple potential. Is very important but very simple. Now, if you want to apply similar method to protein, for example, you cannot really forego the details of chemical structure of protein. We know the protein constitutes of amino acids. The amino acids themselves constitute different atoms, like heavier atoms like carbon, nitrogen, phosphorus, and stuff like that. Let us ignore hydrogen for the time being. So, but even then, if you take all these amino acid structure, etc., then the number of particles in a protein molecule becomes huge. That itself of the order of more than 1,000. But that's not the only thing. Protein is protein. Like when I talk on the protein, that means a protein with a structure that we see in water, in a solution, right? So if you want to simulate a protein, it's unlike other condensed matter systems where a lot of calculations are done in the gas phase. Gas phase calculation of protein is meaningless. You have to calculate a hydrated protein, right? A protein in hydrogen in water. So now imagine that for one single protein molecule, there will be so the number of water molecules would be at least 10 times more, at least. And typically, number of water molecules that we require to hydrate a big protein, let's say big means 100 amino acid long, is something of the order of about 100,000. So now you see that the number of atoms in a protein simulation is something of the order of 100,000. Okay, and that's a huge number. Comparing even today, 100,000 is not a joke. Okay, so one has to run a simulation with 100,000 atoms, including all water molecules and the protein atoms. Then comes in the energy part. That itself is also very important in this context. See, I all the time trying to put analogy and the difference between argon and protein. In argon, because there is no internal structure, then there's nothing called molecular topology, right? But a protein, however, you have a molecular topology because there are many atoms and atoms are bonded in a specific way. So when you're performing simulation over protein, the bonding between different parts of the protein cannot break away. Because if they do, then of course, the protein is no more protein. Similar thing will happen for water. Your water should be maintained as water themselves. So you know that water has got a structure like then oxygen and then 2 hydrogen with an angle of about 109 degrees. So that must be maintained no matter what simulation you perform. Okay, then only can tell is water. And this is not easy. The way that we, people do is that, first of all, the total energy of the system that we require to calculate either energy of the system or the force, because the force is a derivative of the potential, right? So if you know the potential, you take a derivative that will give you a force, and that's precisely what is being done in the programs. So part of the energy will come from so-called bonded interactions. So that means you have covalent bond between, let's say, different atoms in a given topology, and you cannot break the bond. So the bond interaction will be something like an elastic interaction. So when you try to stretch it, it will come back to the original position. And similarly, if you want to change the bond angle, then that will also cost energy. So if you want to make a deviation of bond angle, it should make sure that the bond angle comes back to its equilibrium value. And then there's another thing called dihedral angles. So dihedral angles are like, the proteins have got atoms, and there's a plane that you can define with 4 atoms at a time, which is well defined actually in case of protein. For all molecules is well defined. This particular for molecules, okay, because protein is a molecule, you have to consider all these things. So you have to have a cost of energy by that costs by rotating the atomic plane. So if you take, let's say, 4 atoms of protein, and then you can construct a plane with 3 atoms, you can construct another plane with 3 atoms, and the angle between the 2 atoms, 2 planes. Angle means normal to the planes. How much that angle is subtended, that defines the structure. So there are 3 possible interactions that you have to take care of. One is bond stretching, other is bond bending, you sort of change the bond angle, and the dihedral contribution. We are changing the atomic planes. Okay, so these are the things that we shown in this diagram. On top of that, you have electrostatic interaction, because you know that protein, many part of protein are charged, and hence they will cost, by the movement, they will cost electrostatic energy. So that you have to take into account, and they cannot interpenetrate. The atoms are like solid mass, you can think of like balls. So they cannot interpenetrate, and that is taken care of the van der Waals interaction. So all these interactions that you need to consider in order to find how an atom in a protein is moving. And the same thing is valid when you compute the movement of, let's say, atoms of water molecules. So you can imagine it's a humongous task. And that's why it took so many years after the first simulation on argon was reported to have successful simulation on protein. And that too was a very short simulation. There's only 200 picosecond simulation. And nowadays people do a microsecond simulation. Okay. So, but nevertheless, the trouble that we encounter is similar. So different steps of protein simulations are shown here. It's not really so, this thing. Basically, we start with some protein structure, protein structure here that we take from PDB file. Then we put in water, we add ions to make sure that the protein system is neutral, electroneutral, and then we perform the simulation by following different steps. These are not so important. Let's go to the final result. So this is okay. This is just an example with a protein which is, I think, 150 amino acids long. It's called calmodulin. Now, what is important here, by doing simulations like this, we can generate structure of a protein. Now, what is the structure of a protein? That is important. See, I mean, when we talk about a large molecule like protein, see, all the time I'm using the word protein, but whatever that I'm saying is not only true for protein, but for any molecule, large molecule which is having internal structure. Okay, so colloid are big molecules, right? I mean, like micrometer particles, but they're all particles. They don't have internal structure. Protein is smaller than that, slightly smaller than that. Let's say something about 40 to 50 nanometers typically, but they have internal structure. So this makes the life so difficult. You have to consider the internal structure. That's something I try to tell you. Now, after simulation, you get a specific way, like how the amino acid residues are located in space, and that is given in terms of specific values of the dihedral angles, then the let's say the bond angles, and so forth. Okay, and in fact, this we call it a protein conformation, because and then the conformation may change by different type of events. Like if the protein binds with some ligand, then typically conformation of protein actually changes, and that is important because this change in conformation gives stability to the protein complex. Okay, so this is something I would like to talk about, a protein simulation. So take home message is, first, the simulations that let's say people performed, that was slightly before I was born, and that was actually by taking care of the proper algorithm to make sure energy conservation follows. That's absolutely important. And after that, the next simulation that people performed, well, it does not mean that people are quiescent in between. A lot of things went on. I mean, like people trying to work on different type of algorithms, developing different type of, let's say, chips and those things, so that one can do parallel computation. All these things were going on, right? Things were not quiescent. So then in, let's say, early 1990s, people were successful to generate protein conformation in a reliable way and try to see how the, let's say, different type of interaction potentials can be developed, so that the protein simulation can be performed with success. That means you can compare the experiment. And in protein, the experiments are essentially the crystal structure data. So you can compare the crystal structure data and see whether the simulation can yield that. And this particular force field calculation, okay, so basically what we do here, we take different values of the parameter. Okay, so if I go back to this, yeah, so all these parameters that we use here are taken from different type of calculations, and each of the calculations are extremely, uh, costly. Mostly they are very, very costly. So this is the second part of my talk. Now let me go to the third part. The point is the following. So far so good. People are very happy that you can actually simulate the protein structure and you can do a lot of calculations, etc., etc. But now comes in difficult point. Two things. First, a lot of protein actually are not structured. That's called, well, there are various names for such class of protein. It's called, typically you can say, intrinsically disordered protein. So that means the protein, part of the protein does not stay in the same structure, but it changes from one structure to another structure. So if you want to describe the structure of protein, you cannot describe in terms of, let's say, this is the structure. You have to describe with some probability that this structure may happen, that structure may happen, and so forth. And then it turns out those proteins are pretty active in ligand binding. So functionally active proteins are quite often, if not always, are such proteins where the structure can fluctuate from one to another. Okay, and then the lot of proteins, well, now instead of going into the details of calculation, I can understand what protein structure is going to be from simple argument. See, typically what happens, a protein has got some part hydrophobic and some part hydrophilic. So as a normal tendency of energy minimization, hydrophilic part will be exposed to water and hydrophobic part will be coming inside. And that's a typical driving force of a protein to take a structure in the solution phase. And that's precisely what is simulated in this kind of, all simulation of so much of cost. So we are not really doing something so marvelous because this is something people would expect anyway. But it's important because that gives a quantitative idea what is happening. What I'm saying is qualitative, right? Now quantification, it becomes very important in many stages. And those proteins, okay, now there are proteins where by some misfolding, the hydrophobic part gets exposed, and once they get exposed, such proteins actually assemble together to make some kind of assembly, and those assemblies are quite often, so these are misfolded, right? So they're not good for our health. Most of the, let's say, nerve degradation disease like Parkinson, Alzheimer, they're all connected to formation of such assemblies. So it's very important so far the health issues are concerned, like how to understand how the aggregation takes place. Now the problem to understand aggregation does not mean just one single protein. It means several proteins together in the solution, right? So if you want to study aggregation of the system, you have to study many proteins together. And single protein, as you could see here, is so difficult a job. So if you want to study an aggregation in computer simulation, then this kind of standard technique that I described, where you take all possible atoms and force field, etc., they are so costly. I'm not saying they are impossible. Technically, this is certainly correct, but practically, such calculation takes such an enormous amount of, let's say, computer resources that it becomes extremely difficult to carry out such calculations. So people have been trying, as a result, something is a possible solution that you do coarse graining. Now, what is coarse graining? Coarse graining means you don't consider all the atoms per se. You take a group of atoms and represent by one kind of pseudo atom. Okay. So once you do that, the number of, let's say, atoms that you need to consider to describe the protein actually decreases. Okay. And in this kind of approach has been taken by many force field developer like Martini, then Sira, many force field that has come up nowadays, where you don't treat all the atoms of the protein, but you take a group of atoms and consider that group as one pseudo atom and consider the protein structure considering those groups of atoms. But there's a problem, like, first of all, if you do this, then the atomic planes, look, in a protein, I told you that the most important feature is that the atoms in a protein has got well-defined planes, like, and so these are called backbone angles, for example, which is phi and psi, and okay, that's something I should have told you, that depending on the backbone angles, the protein can be having at least three different structures. One is the alpha helix, like they form like helical screws, or they can be beta sheets, parallel lines like this, or they can be random. Okay, these three, and that depends on the specific values of the dihedral angles. And this was first demarcated by an Indian, Ramachandran. So we call it Ramachandran plot. So now this building up a Ramachandran plot by using this model becomes almost next to impossible, because you don't have the atomic angles. Okay, so dihedral angles are not defined here. You take the atoms as a single entity, right? You can people define some pseudo dihedral angles, like taking dihedral between those big chunks, but these are nothing to do with the backbone dihedral angles per se. Now, if you want to describe a protein which actually deviates from its canonical structure, and those are the proteins which actually participate in a lot of functions. And if you want to describe the opening of the hydrophobic residues to water, then obviously hydrophobic residues undergo changes in conformation, otherwise you cannot get exposed, right? So in a word, if you want to describe such systems where the protein deviates from its, let's say, canonical structure means the structure in which we know normally, like the hydrophobic part is buried inside and hydrophilic part is exposed outside. Such structure is the protein undergoes deviation from such structure. And if you want to describe this kind of systems, mostly people describe in terms of extremely coarse-grained things, like they take the protein as a unit and then describe how this structure is going to aggregate. This is okay, but this is very, very coarse-grained structure. So can we do slightly better than that? So the way that we shall like to do here is something that we proposed is the following. So let me just try to explain this picture, and that will also sort of tell you what we mean by the coarse graining that we are trying to perform. So in this coarse graining, we are trying to make sure that the dihedral angle informations are retained. It's a difficult task. Why? Because as I told you, in the coarse graining, you don't take the atomic planes per se. So what we do here, if you look at those big spheres, they represent an amino acid residue. In what way? That if you take, let's say, crystal structure, an amino acid will have its center of mass, and then if you compute the distance of the heavier atoms from the center of mass and square them up and add and take a square root, that will give you kind of a radius of those of that amino acid. And this radius is typically 3 to 4, something between 3 to 4 angstroms. So that's fairly constant, uniform for different residues. And so one sphere represents the center of mass calculated in this fashion and the radius of gyration calculated from the crystal structure. Okay, and there's a springs. The springs actually represent the stretching and bending angle between different parts of the protein, which I shall come in a minute. And then what we do, we assign for each sphere with extra degree of freedom, which are the angles, which is very similar in our physics community. We call it XY model. So it's just like saying that when you update a sphere, then update its position and update the angles associated with this. But once you try to do that, and of course you have the bits can be of two types. So these bits are solvophilic bits and these bits are solvophobic bits. How the solvophilicity and solvophobicity is taken into account, I'll come back later. So the question that we are asking here, that if we make sure that solvophobic and solvophilic bits are different in some way or the other, and if we assign the dihedral angles and take the dihedral angles and additional degrees of freedom, can you reproduce the structure from Ramachandran plot? So you see, this is coarse graining in what way? Because they are not considering all the atoms. They are considering one residue as one bit. But it is having structure information in what way? An additional variable that is defined with respect to the bits. Okay. So now we compute different interaction by using all atom simulation trajectory. So suppose you have a protein for which you know the trajectory, have the trajectory in hand. Then what you can compute is the bead radius. You can compute by computing the radius of guidation for different beads over the trajectory for different confluence of trajectory, and you get a statistics. And if you convert this into energy, which you can do by taking log of the probability and multiplying by kBt, so that will give you some kind of energetics, and the minimum of this energy will give you the radius of the bead. Then for the stretching, you can compute the distance between the two beads, and again statistics. You take the minimum, and that will give you the stretching energy, and of course multiplying by the kBt. Then again you can do the same thing for the angle. What you do, like you now take center of mass of successive 3 beads and calculate the bond angle between them and take a statistics. So that will give something like this, and minimum is again the energy for the bond stretching. And okay, from the curvature at the minimum, which you can compute from the second derivative of the energy profile, that will give you the values of the spring constants. So then this way you know all the spring constants for the system. And in a similar way, you can compute all the energy parameters from in different ways. Now the way that solvophobic and solvophilic are distinguished come from here. So if you compute the probability of water oxygen, okay, we define the water molecules by oxygen atoms only, so we don't take care of the hydrogen bonding, for example, but that's an approximation which we are working with a simple model, right? So so basically what happens that this has got a well defined minimum. In case of a okay, we are not calling it hydrophilic or hydrophobic because we have only oxygen molecules as our solvent. So we call it solvophilic or solvophobic. Solvophilic means it loves water molecule oxygen atoms, and solvophobic will mean they hate the oxygen atoms. So if you look at the density profile and make an energy scale out of this, then the form of the energy is different. For solvophobic, it is like repulsion potential. That's something to expect, that a solvophobic bead will not like the oxygen atoms, right? So it will try to repel, and this is the kind of form of repulsion. And for solvophilic, however, they will like to have oxygen atoms in its vicinity, and the energy is given something like this, where those parameters can be sort of estimated from the trajectories. And you can okay. Next thing, what is important, see, so far giving the let's say the residue in terms of bead, etc., is pretty standard. People have done that earlier. In fact, all the Martini, Syrah, on those force fields that people use, they use similar type of approach. The real difference comes in when we try to include the dihedral angles. So what we do is the following. Let's say we have the all-atom simulation trajectory, and from the trajectory we can compute the dihedral angles of different residues in the protein, okay, and we can calculate statistics, but these statistics will be two-dimensional. You have two, okay, now it turns out the protein backbone can be given in terms of two dihedral angles which are called phi and psi. Okay, so these are, okay, don't bother too much the how exactly phi and psi is defined, but all that's important that you can compute those angles and calculate the joint distribution of phi and psi over the trajectory. And if you take this joint distribution, then you can convert that into energy scale, and if you make a contour plot, they will look like this. Now what is important here, for solvophilic and solvophobic, the contour plots are different. So now the solvophobic and solvophilic categorization are done based, first of all, this categorization is done in a simple way. In our calculation, all charged residues at a given pH in the medium are taken to be solvophilic because they have charges. All other residues are solvophobic because they don't have charge. So they won't like water so much compared to those with the charge. And so that we know, like for example, if you give a pH, then it is possible to tell that these residues are charged and these residues are not charged. So based on that category, we calculate those, let's say, the interaction between the solvophobic or I'm using hydrophobic, hydrophilic and solvophobic interchangeably because they're same so far this model is concerned. So we compute the actually oxygen atom distribution about the solvophobic and solvophilic bits and compute the energy scale for these two bits separately, and also for the dihedral angle we see that those energy scales are different. Now we put in those informations into our calculation. So we are not considering anything directly on what is the energy scale between different structures. We are just saying this is solvophilic or solvophobic because we know that in the end, the driving mechanism for protein to get its structure is the fact that solvophobic will like to get buried and solvophilic part will like to get exposed. Do we see something from here, and can we now calculate the Ramachandran plot for the system? That's what we are trying to ask. Now, in order to perform this, we do a Monte Carlo simulation because that's easy. A Monte Carlo simulation, good thing is that you don't compute the dynamics per se. You just know the energy, then you make some change in the let's say degree of freedom, and from the cost of energy you can compute whether the change is going to be accepted or not. So this scheme is something very simple. We take some initial configuration. For us, the initial configuration will involve the position of the bits and the dihedral angles, which we calculate from the, let's say, from the crystal structure. Okay, and once we do that, and we also know the Coarse-Grained parameters for the Hamiltonian. Now again the parameters are similar, like we take in consideration of, let's say, the stretching, bending. Dihedrals are taken in terms of the probability distribution that I told, the joint distribution. Then we have the charge interactions, etc., etc. The solvent interaction given by solvophilic and solvophobic beds, and the solvent-solvent interactions taken to Lennard's type. So this is a simple model, and then we calculate we change the position and dihedral degrees of freedom, and then compute the energy by looking at the parameters of the system, of the Coarse-Grained parameters that we can compute it, and if the energy is less, then we accept. If not, then we use this as in terms of Metropolis algorithm, where we do, like, we compute the Boltzmann factor, we draw a random number between 0 to 1, this is all done in computers, and then given this like kind of property, like if this Boltzmann factor is larger than 1, then we accept the new position. If less than 1, we reject. Then we go back again to the generation random numbers. So that's the basic algorithm. Using this algorithm, so this is first example that we have tried. So this is a protein which actually is called GB3 protein, which is a very simple protein with 56 amino acids, and for the crystal structure is pretty well known. And this protein is used as a model protein because of small size, to understand different structural properties of the protein, etc., etc. So for this protein, we do the same thing, like, there are 56 amino acids in the protein, so there will be 56 beads. Now for 56 beads, we require this many solvent, oxygen atoms, to solvate it properly. And once we do that, we calculate the Coarse-Grained potentials, like, the bending angle, the bond distance, stretching constant, bending, the bond angle, bending constant, and then dihedral potentials, and all other non-bond interactions, including the charge interaction, etc., etc., and do the simulation using Monte Carlo. See, the all-atom simulation was done using MD with all details of interactions. Here, the simulation is done using the Coarse-Grained Hamiltonian and using the energy that we derived from the all-atom calculations and using Monte Carlo scheme. What we find here, like 80% of the structures are reproduced correctly, particularly alpha helix is produced 90%, beta sheet is produced 88%. Things are not so well if the structure is random, is coil-like structure is not produced so well. But so when the structured part is concerned, it is reproduced extremely well. So this actually gives a confidence that this kind of scheme can actually reproduce Ramachandran plot extremely well. Okay, and this is where our simulation scheme is better compared to the existing schemes, because the existing scheme, the Ramachandran plot cannot be generated directly. You have to backmap the Ramachandran plot using the information that you gather from the simulation. But here, you get the Ramachandran plot directly from the simulation. So that way it is much faster. Okay, and and also is a single, is not like a multiple atom approach. It's a single atom approach, because you have one single bit representing the amino acid, but you have additional degree of freedom corresponding to the dihedral angles. Okay. Now we apply this kind of scheme to, so far what we showed, the structure of a folded protein or the well-folded structured protein can be reproduced, and Ramachandran plot could be comparable, particularly a very good agreement between different structured elements. Now what happens for an IDP? Because I told you that the main point that we started doing this calculation is that we would like to see how a protein solution is going to behave. So if you have multiple proteins, then can the protein solution aggregation phenomena can be described in terms of this kind of model, which is not fully coarse-grained, like taking protein as a unit, not all atom where you take all the simulation, all the atomic interactions, but something in between, which is doable by current days computational power. So a protein that we have considered is something called alpha-synuclein, which is a protein which actually can form aggregation, because this is the part which is unstable, and this is the part which actually undergoes structural fluctuations, and as a result of that, this protein is prone to aggregation. Now, experimentally it turns out that this part can bind to different nanoparticles. For example, we will have seen zinc oxide nanoparticle can bind, this part can bind to zinc oxide nanoparticle, and once bound to zinc oxide nanoparticle, the propensity of formation aggregation actually goes down. Okay, so if so, that will mean that the core region actually gains stability, because you see if the core region is unstable, then there's a probability that core region will go from alpha helix to beta sheet, and then beta sheet can combine together to form a structure. But if it is inhibited, like if the alpha helix is stabilized, then such a propensity will be less, because it's not possible for the system to go to beta sheet conformation. And this we check with our model. So the way that we do is the following. First, we perform some all atom calculation. We find these are the structures for the protein without nanoparticle, and then with nanoparticle the structure becomes something like this. So the helix is still maintained. And on top of that, we know from the all atom simulation which residues are responsible for the binding to the nanoparticle. Okay, and experiment is also known to some extent, and we get a good agreement. Now what is? Yeah, because the nanoparticle, okay, zinc oxide nanoparticle, right? So some oxygen site, some zinc site. So oxygen site is electronegative, and this particular region of protein where it binds, like this region, they're rich in basic residues. So by electrostatic they can bind. Okay, and once they are bound, then the other region gets stable actually. So more like an allosteric protein. Okay, so now what we do, we run, and from the simulation we estimate the Kb, B, K. Okay, so this is the stretching constant, this is the bending constant, and more importantly, for nanoparticle binding case, what we do, we know for the bound system, the residues will have less degree of freedom, so they cannot move much, right, because of the binding. So now what we do, we know the binding residues from our simulation, right, tolerance simulation, also from experiment. We take those residues to be fixed. That means when the other residues are performing their motion through change in position and the dihedral angle, the other residues which are binding residues, they are kept fixed. Neither the position nor the dihedral angles are going to change. Now what we look at, what is happening to the region which is, let's say, the known to be the region responsible for the binding, whether that region gets stability or not. So this is where we show, okay, don't bother so much about the mathematical details. The green ones actually will mean that those residues are stable. Okay, and what we are particularly looking at is the stability of the region. Okay, so if I go back to the picture again, so in this region, stability in this region. So this is the data that we get from the all atom simulation. So these residues are stable, the green ones are stable, and this is the data we get from our all atom calculation, from the coarse-grained calculation. So you see the, well, I mean, I'm not going to compare, number wise, but overall the stability is very, very similar in as we can get from the all atom simulation. From the coarse-grained simulation. So the data is pretty comparable with the coarse-grained and all atom simulation. So the lesson that we get out of this calculation is indeed the binding of the nanoparticle at the nanoparticle binding region of the protein helps the other core region to get stabilized. And this could be a mechanism by which the formation of, let's say, the aggregation of the protein would be inhibited, which is experimentally observed. Well, so take home message is something that I am not going to sort of repeat again. And of course, let's say we have, okay, maybe I should stress that point. Say in the entire calculation, we have taken only hydrophobic, hydrophilic type residues. Other things are almost uniform, right? So the binding constant, the stretching constant, etc. The bending constant, stretching constant are essentially similar. The difference is actually in the hydrophobic and hydrophilic bits, how they interact with water, right? And that is, and also the dihedral interaction depends on if this is hydrophobic or hydrophilic. And that is good enough to give it a structure. And that is also good enough to describe the stability of the disordered protein under bound conditions. Okay, and these are experimental known facts. Okay, now, okay, so far we have reproduced whatever that is known experimentally. But what are the new things that we can do? That's something in proposal form, because we are, see, this is an ongoing project. So for example, if you have now what you do, like again, our classification will be based on hydrophobic, hydrophilic, nothing else. So suppose you have pair of proteins, and for the pair of protein, we shall perform the coarse-grained simulation, because we know that for a single protein, coarse-grained simulation works extremely well. And let us assume that the same thing is true if you have a pair of proteins. So for a pair of proteins, you can calculate the interaction between the hydrophobic part, hydrophobic hydrophilic part, hydrophilic part. So there are three categories of interaction. Okay, and once you have those interactions in your hand, from this kind of calculation, we call in the language of statistical mechanics, we call effective interaction. So effective hydrophobic, effective hydrophilic, effective hydrophilic interaction. Now we shall simply forget the solvent. Now all the effects of solvent, etc., are taken into account in the effective interactions. So now what we have are several such proteins, but only these three categories of interactions are there, and of course there are dihedral interactions and other elastic interaction coming from the stretching, bending, etc., etc. These are all same for all the proteins. So now the question is, does it describe, let's say for binding even, for aggregation, it turns out the beta regions actually come close. So that will mean if you compute the beta strand distance between different proteins in this system, that the distance, the probability will be much larger, right, compared to other components like hydrophobic, hydrophilic. Answer for the two protein case is yes. We have already done for two protein case, which we are in the process to write a paper. And next thing that we shall try, we shall apply this method to many such proteins. And second thing, that so far everything is equilibrium. One thing I should tell you, the Monte Carlo simulation can give extremely good results on equilibrium. MD can give information on equilibrium as well as on dynamics. So that way MD is advantage. But advantage of MC is that you don't have to compute the derivatives, and that makes your life extremely simple. Is enough to calculate the energy, and then you can actually constitute moves, etc., which can easily be implemented. So implementation wise, MC is good. Now for this kind of system, we shall try to develop in order to understand kinetics, we shall develop something called Brownian dynamic simulation, where the degrees of freedom will be associated with, let's say, protein, well, in our language, the position of the bid and dihedral angles. So we just write a kinetic equation which is similar to Brownian dynamics equation and solve it numerically to get the kinetics. So that's something we are planning to do maybe in next few years. So I stop here, and any question, any doubt, please.
Hello, sir.
Yeah.
In previous slide, you have mentioned somewhere for simulation, they will require energy minimization steps.
Yeah.
And addition of hydrogen atoms. Why, sir?
Okay, they are not so important. Hydrogen atom is required because there's hydrogen atoms in the system, right? In our coarse-grained simulation, we don't take care of hydrogen atoms because it's my own, let's say, bias, you can say, that none of the classical simulation can take care of hydrogen atoms properly. So simply forget them. And none of the dihedral angles, etc., that we define involves hydrogen atoms. So we don't consider them. But in practice, hydrogen atoms should be included because there are hydrogen atoms right in the system. That's all about it. In fact, let's say many force field like Gromax, they don't consider hydrogen atoms separately. They just take hydrogen atom to be so-called united atom model. This is sort of in a part of some heavier atom. Like methyl group is taken CH3 itself. So the methyl is just one single group. So, but in the older version like NAMD, etc., there the hydrogen atoms are taken separately.
That's I wanted to know because the organic molecule itself has hydrogen atoms. So we are adding additional hydrogen atoms.
Look, I mean, it all depends. Again, I should admit, none of the classical simulation can deal with hydrogen atom properly. Okay, so everything that is done so far the hydrogen atom is concerned ad hoc. Okay, so all the hydrogen atom addition, etc., is purely ad hoc. There is no good way of doing proper physics of the system. They're all ad hoc, and minimization is required for a different reason. See, it's a complicated system, right? And we know that in order to get a structure, for example, is a truly speaking, is the minimization of the multidimensional space. And that's why AI is now used in these kind of things. So a minimization of multidimensional space is always very, very dangerous. Like I know myself, like I was trying to minimize something with 50 variables, not for this kind of problem, it's a different problem. And it's really a danger, I'll tell you. It's so difficult. And in this system, the dimension is as many atoms are there, right? So what people do, doing some simple Monte Carlo steps or energy minimization, they take the system as close to the actual minimum possible. But if you don't do it, nothing goes wrong. So you can actually safely even ignore this.
Is it possible to actually simulate a full reaction using this? Like, for example, a hydrothermal reaction or something like that?
I haven't thought about that. Well, I mean, I wouldn't say anything because I haven't really thought about it. So all the time, my attention was on this kind of aggregation of protein. I don't really know. Yeah.
Something completely new to me.
Uh-huh.
I just want to know if I'm on the same page. So when you for example, you're simulating a single protein.
Yeah.
So whatever parameters you have said, like bond angles,
Hmm,
dihedral angles,
yeah,
and
yeah.
bond angles, all those. So you predict them from your prior knowledge, like for the input, or
Yeah,
it is
the
something
input
you
is taken.
compute?
Well, I mean, those constants we compute from the all-atom simulation and use them for doing the coarse-grained simulation. One thing I didn't tell you here, it turns out for many cases, because I cannot tell you the final word on this, appears to be transferable. Suppose you take a long simulation, all-atom simulation for let's say GB3, and then you plan to use the GB3 for another protein, like ubiquitin is another example that we tried, and it appears to work fine. But it does not work fine for an IDP. Okay, so now exactly how it works, like how much is transferability is valid, something we do not know.
That means the accuracy
A bit less, yeah. How does it matter? If it is instead of 88%, it could be 80%. It could be 75%. It's fine.
For
Yeah, okay, this is a question and then I come back to you.
I saw that in some place you showed that when you are attaching this binding it with the zinc oxide
Yeah.
nanoparticle. So in this kind of simulation, which you told before that something which has an internal structure, you probe it using this molecular simulation. So how do we impute the nanomaterial, a nanoparticle in that simulation, since it contains 17,000 atoms to be precise?
Yeah. See, in this calculation, the zinc oxide nanoparticle is taken to be a single unit, and we take them fixed. The protein is moving in its fixed environment. So that is what we do. But in principle, you can take like some kind of vibration, etc. in the nanoparticle, but that will like make your life extremely complicated. So all that we wanted to see, if I take this simple approach, can we reproduce experimental non-binding residues? And we could. And it does not violate our intuition that it should be done via electrostatics, and that is also follows. So we're happy with this. But in principle, it should include those movement of those atoms. Yes. Yeah. Okay. For the all atom simulation, time step was 2 femtosecond.
And what was the total duration?
You mean for this calculation? Yeah, microsecond. Yeah, nowadays no one takes buy your data below microsecond. Okay. That depends. If you're happy with structure or the static properties, MC is good enough. But if you want to look into the dynamics in addition, then you have to perform MD. But typically what happens, people combine MC and MD. So first they do a little bit MC and then they go for MD.